All right, the last section that we're going to cover is chapter 9, 9.1. And this is kind of where the second part of statistics, if you are to transfer to a senior college, this is where they will pick up, and it will be with hypothesis testing. This is really, really big. This is kind of where we do all of our analysis on determining if certain statements are true or false, or more geared toward us looking towards another type of solution to a problem, okay? So we're not going to go that deep. I just want to make sure I explain two types of hypothesis to you, and then we're going to do a very general hypothesis test, okay? So you see there's a whole bunch of words, and I'm going to explain more so through the examples. Now, the two hypotheses that I need you to look at will be the null hypothesis and the alternative hypothesis, okay? We're going to write hypothesis statements using symbols. When you write the null hypothesis, you will write it such as H sub O colon U equals, okay? And that lowercase u, you know, stands for population mean. It's going to equal some number, okay? But the key there is making sure that you can see. You will write that H sub O colon U equals whatever the population mean is. Kind of like your general statement. Our alternative hypothesis will be written with H sub lowercase a. H sub a. And it too will begin with colon lowercase u, and you'll have some type of symbol and some number, okay? Now that symbol will constitute what type of test we are talking about. And there's three main kinds. You have a two-tail test, a left-tail test, and a right-tail test. And I'll get into those when we get into the actual examples. This sheet you should have, so you should be able to follow along with me. But I have three examples that I want to show you guys on how to pick out that null hypothesis, that alternative hypothesis, and determine what type of test we're talking about. Now, if you look at example 1, this first one, it's talking about a snack food company. And it says this snack food company produces 454 gram bags of pretzels. Although the actual net weights deviate slightly from 454 grams and vary from one bag to another, the company insists that the mean net weight of the bags is 454 grams. As part of this program, the Quality Assurance Department periodically performs a hypothesis test to decide whether the packaging machine is working properly. That is, to decide whether the mean weight of all bags packaged is 454 grams. Now, you and I both, we eat chips. You might prefer pretzels. But anytime you go buy your chips or your pretzels, you know sometimes the bag has a lot of chips in it or a lot of pretzels, and sometimes very few, okay? All of that is done through a packaging machine. So the company sets that machine at a certain weight, okay? Now, that doesn't mean that you're going to have 20 chips in that bag or 20 pretzels in that bag each time. It depends on the weight of the bag. So that's how your number inside the bag, your pretzels number, chips, deviates, because it's being processed through a packaging machine. So A says determine that null hypothesis. So the null hypothesis would just be the general statement. What did this company say was the net weight of their pretzels? So you would do H sub O colon U equals 454 grams. That's my null hypothesis, that the weight equals, the mean weight equals 454 grams. Now, the alternative on B, what would that alternative hypothesis be? Well, you have to look for certain keywords that let you know the direction in which you are going. Direction means left or right, or I could be going both ways, okay? So with that being said, the key word here is deviate, okay? It doesn't specifically say less. It doesn't specifically say greater. It says that the weight deviates. So deviating means it could be greater than 454 grams, your weight, or it could be less than 454 grams. You can go both ways. It's not being specific. So your alternative hypothesis would symbolize that. It would be H sub A colon U. Now, I'm going to use the symbol, the not equal to sign, 454 grams. Now, you use the not equal to sign when you don't know the direction. If it doesn't specifically say less, less than, smaller, or specifically say greater, greater than, exceeds, those are keywords to let you know that you're going higher, then you're going to say, well, it just doesn't equal that number. Okay, that will be your alternative. It just doesn't equal it, period. So with that being said, here we have the question on C about your type of test. Your type of test is going to explain your direction. So it does not say anything about being left, and it does not say anything about going to the right. But I will say this one is two-tail. Two-tail means I can go up as well as I can go down. So this particular example is a two-tailed test. All right, let's look at the second example. It says the R&R Boecker Company of New York collects information on retail prices of books and publishes the data in the Boecker Annual Library and Book Trade Almanac. In 2000, the mean retail price of history books was $51.46. Suppose that we want to perform a hypothesis test to decide whether this year's mean retail prices of history books has increased from the 2000 mean. So, that null hypothesis is going to be your general statement. We're talking about history books, so what is that price? So we're going to say H sub O colon U equals $51.46. That is the mean price of history books back in 2000. Now your alternative hypothesis, we're looking for keywords to show direction. So it says, suppose we want to perform a hypothesis test to decide whether this year's mean retail prices of history books has increased. That's your key word, increased from the 2000 mean. So our null hypothesis would be H sub A colon our U, and this goes back to our algebra. When you're talking about increase, we're going to use the greater than symbol, $51.46. So increase, that's going to be symbolized with the greater than. So if you're looking at to classify what type of test this would be, then you can only specifically talk about the right side, because we're looking at stuff that's greater, bigger than $51.46. So that would be a right-tailed test. The next example, calcium is the most abundant mineral in the human body and has several important functions. Most body calcium is stored in the bones and teeth where it functions to support their structure. Recommendations for calcium are provided in dietary reference intakes developed by the Institute of Medicine of the National Academy of Sciences. The recommended adequate intake, RAI, of calcium for adults ages 19 to 50 is 1,000 milligrams per day. Suppose that we want to perform a hypothesis test to decide whether the average adult with an income below poverty level gets less than the RAI of 1,000 milligrams. So we're looking at our general statement, our hypothesis. It says that the recommended adequate intake of calcium for adults is 1,000 milligrams per day. So we're going to say that our null hypothesis is going to equal 1,000 milligrams. And then our alternative hypothesis tells us our direction. So we're going to look, and it says less than the 1,000, okay? So our alternative will be HA colon, if we're talking about less than, then going back to algebra, that would be actually the less than sign of 1,000 milligrams. And very obvious, if we're talking about what type of test, if we're talking about less, we're on the left side. So this would be considered a left-tailed test. All right, now let's actually perform a small hypothesis test. All right. Here you have on number 1, we have childhood participation in sports, cultural groups, and youth groups appears to be related to improved self-esteem for adolescents. In a representative study, a sample of N equals 100 adolescents with a history of group participation is given a standardized self-esteem questionnaire. For the general population of adolescents, scores on this questionnaire form a normal distribution with a mean of, that's population mean, of 40 and a standard deviation of 12. The sample of the group participation adolescents had an average of 43.84. Does this sample provide enough evidence to conclude that self-esteem scores for group participation adolescents are significantly different from those of the general population? Use a two-tailed test where alpha equals 0.01. All right, now this is very simple. It's a lot of words, but you need to determine if there's enough evidence to keep our null hypothesis or reject the null hypothesis. Those are the terminologies that we use with hypothesis testing. You either are going to reject the null. Rejecting it means you don't want the null hypothesis. We're going to go with the alternative hypothesis. Or you're going to keep the null hypothesis, which means we're going to stay with it. It's not enough evidence for me to go to a whole nother hypothesis. So first, I also should, I attached in Canvas, and I'm going to switch. All right, in Canvas, I attached your last and final different graph. Well, not it's a graph of a bell, but it also has some very good information, kind of like a chart for your alpha levels, okay? These are levels of significance. So you have on this chart where alpha is 0.05, you have something called boundary, critical boundary areas. And the critical boundary areas for 0.05 would be from negative 1.96 to positive 1.96. That would represent alpha being at 0.05. When you're at alpha 0.01, you have the critical boundary of negative 2.58 to positive 2.58. And when you're at alpha 0.001, we have the critical boundaries of negative 3.3 and positive 3.3. So these critical boundaries, if you're, and we're going to call them z-scores, okay, but it's a different little formula for finding the z-scores for your critical boundary areas. Now, with these significant levels, levels of significance, I should say, if your z-score, and like I said, it's a different formula that we're going to use. It's not the same as our Bell. It's slightly a little different for finding the boundary region area. If it falls within the critical boundary numbers, then you will keep your null hypothesis. If that particular number is on the outside of your critical boundary numbers, then you must reject the null. Okay, so we're going to come back to that. Let's do some plug-in on our first example of our hypothesis testing, and I'm going to also give you the actual formula for finding this particular z-score. So that formula is, we're going to take the sample mean minus the population mean divided by the standard deviation, which is divided by the square root of n. So let's do some plug-in. We're going to take, and I have it kind of italicized for you. We're going to say our sample mean is 43.84 minus the population mean of 40 divided by the standard deviation of 12, which will be divided by, and we're dividing by the square root of n, which is 100. So we're going to subtract 43.84 minus 40 will give us 3.84 divided by 12 divided by the square root of 100, which we know is 10, will give us 1.2. So when you divide 3.84 by 1.2, we get 3.2. Okay, so that's the z that we're working with, 3.2. Now, it says that we're going to use a two-tailed test where alpha is 0.01. So if we look at our Bell at 0.01 level of significance, our critical boundaries are from negative 2.58 to positive 2.58. So we know, and I'm going to write this here, at alpha 0.01, we have negative 2.58 to positive 2.58. So we're going to look at 3.2. Obviously, that number does not fall within that range. That number would be on the outside. 3.2 is bigger than 2.58. So since it's on the outside, the term that we're going to use is that we are rejecting the null hypothesis, okay? We're rejecting the null. So if you wanted to answer the question properly, it says, does this sample provide enough evidence to conclude that self-esteem scores for group participation adolescents are significantly different from those of the general population? And you would say yes. Yes, the sample provides enough evidence to conclude that the self-esteem scores for the group participation adolescents are significantly different from the general population due to the fact that it did not fall within your critical boundary areas. If our Z number would have been 2.5, then we would say no, there's not enough evidence because it would be within that range of numbers. Does that make sense? So here, all you're looking at, once you plug into that Z-score formula, you're going to say, hey, does that number fall in between my critical boundary numbers, or is it outside my critical boundary numbers? If it's in between, we would keep. If it's on the outside, we reject. Let's look at the next example. It says a researcher is evaluating the effectiveness of a new physical education program for elementary school children. The program is designed to reduce competition and increase individual self-esteem. A sample of n equals 16 children is selected and the children are placed in the new program. After 3 months, each child is given a standardized self-esteem test. For the general population of elementary school children, the scores on the self-esteem test form a normal distribution where the mean is 40 and the standard deviation is 8. So on A, it says if the researcher obtains a sample mean of 42, is this enough evidence to conclude that the program has a significant effect? Assume a two-tailed test where alpha is 0.05. So let's get that Z. So we're going to take our sample mean of 42 minus the population of 40 divided by the standard deviation of 8, which will be divided by the square root of n, which is 16. Now, we do know that the square root of 16 is 4. So 42 minus 40 will give you 2. And 8 divided by 4 is also 2. So we get a Z-score of 1. So let's look at our Bell. And we're talking about an alpha level of 0.05, and that's what we have there in orange. Its boundary levels are from negative 1.96 to positive 1.96. So our critical boundary areas for that significance level is from negative 1.96 to positive 1.96. So I would hope that you see that 1 would be in between. 1 is not bigger than 1.96. So it's going to fall in the middle. It's going to fall in between that range of numbers. So if that's the case, then we must keep the null hypothesis. Okay? We are keeping our null. It falls within our range, so we keep it. So if you were answering the question properly, it says, is this enough evidence to conclude that the program has a significant effect? No, it's not enough evidence. It's not enough evidence for me to go with an alternative. So that would be keeping the null. Now, part B is using the same information. N is going to be 16. Our population mean is going to be 40, and our standard deviation is going to be 8. The difference, the change, is I'm changing that sample mean to 44. So I'm saying, okay, let me increase my sample mean from 42 to 44 and now see if there is a significant effect. So let's find that Z. So we have 44 minus 40 over 8 divided by the square root of 16. So instead of a 2 on top, you have 4. And we still have 2 on the bottom. So this time, our Z will increase to 2. Now, I'm still at a significance level of 0.05. So that would mean that we are still looking at the critical boundaries of negative 1.96 to positive 1.96. So by me increasing it to 44, we have now bounced outside of my boundary. Do you see that? 2 is slightly bigger than 1.96. So this time, by me just increasing that sample, now we have to reject the null hypothesis. And to answer properly, is this enough to demonstrate a significant effect? Yes. If I increase it from 42 to 44, I now have a significant effect for me to reject the null hypothesis. And this will conclude what we're going to do in Chapter 9. This was a basic showing you how to do a hypothesis test. I'm not going too deep into it. I just wanted to present it. It's kind of like an introduction to hypothesis testing. But I hope that you'll be able to pull out those null and alternative hypotheses. And if you were to perform a two-tailed test, you could look at those critical boundary areas and know if I'm inside them, I will keep my null. If I'm outside them, I will have to reject that null.